we introduce you to CaRLi-V, a pipeline that estimates dense 3D velocity readings of the environment represented in the form of an augmented point cloud. Velocity values are individually computed for each point to create a dense velocity field that captures detailed movement of objects in the scene. To do this, we use a novel camera, radar, and LiDAR fusion approach to combine radial velocity information from the radar, tangential velocity estimates from the camera, and positional information from the LiDAR for precise velocity estimation. To this end, the raw ADC radar data is processed into a novel velocity cube representation, which directly represents radial velocity readings at all measured points in space, retaining much more spatial and velocity information than the more traditionally used radar point cloud. By projecting the LiDAR points into the radar velocity cube, one is able to extract radial velocity estimates for each individual LiDAR point. At the same time, the LiDAR points are projected into the camera image used to obtain optical flow estimates for tangential velocity estimation of each point. These two velocity vector estimates are combined through a closed-form solution for the full velocity computation, allowing for point-wise velocity estimates in 3 dimensions for all points from the LiDAR point cloud. To test and validate the performance of the proposed pipeline, a custom-built sensor rig integrating a Z2i camera, a Hesai QT128 LiDAR, and a VMD3 radar was assembled. This sensor rig was used to collect a custom dataset. As to the author's knowledge, existing datasets including these 3 sensors either lack ground truth velocities or provide radar in point cloud form only. The dataset consists of scenes with different motion patterns, including people walking around, waving, crossing each other's paths, and moving radar retroreflectors in the environment. Dense velocity estimates enable the extraction of rich motion information from non-rigid dynamic objects, such as when interacting with humans, in a way that is much more informative than the traditionally used rigid object tracking algorithms. Our pipeline is available as an open-source ROS2 package, along with a dataset and evaluation code used to test the pipeline. These can be accessed through the link shown on the screen.